Alright, so welcome back to the OneClass channel. Again, my name is Joey. I'm going to be your chemistry teacher for the session. If you're joining us for the first time, what we're doing here is we are going through kind of frequently asked problems in the secondary school level as well as in the university and college level. And what we're doing here is that we're going to verify some commonly asked problems in both chemistry and also mathematics. So what we're doing here is within the next hour, I have about 10 problems for us. I don't know if we'll get through all 10, but I'm going to do my best to do so, sorry. And what we're going to do is we're going to verify these solutions, and I'm going to kind of teach you the concepts through those questions as well. If you're tuning in for the first time, my name is Joey. I'm currently a Ontario school educator with OneClass, and my teachable subjects are chemistry, music, and as well as I'm hoping to teach, I'll be able to teach math in about a month or so. So without further ado, let's get started on today's problems. I have about 10 problems for us today. All right, so the first question, I believe I've already finished this problem before, and it's kind of a repeat from maybe one of the streams from last time, but it's asking here, a solution containing a mixture of metal cations was treated with dilute HCl and no precipitate was formed. Next, H2S was bubbled through the acidic solution. A precipitate was formed and was filtered off. Then the pH was raised to about 8, and H2S was again bubbled through the solution. A precipitate again formed and was filtered off. Finally, the solution was treated with sodium carbonate solution, which resulted in no precipitation. Which metal ions were definitely present, and which were definitely absent, and which may or may not have been present in the original mixture. So let's look at the solution here, and these are the cations that they give you, these metal cations. And we can look at the solution here. So let me maximize this. Let me zoom in for a little bit and see if we can kind of figure this out here. So it's asking here, so we have first, I like this graph because it actually breaks down all the possibilities of which all the cations may or may not exist. So it says here, aqueous mixture of cations here. If I have HCl and if it precipitates, if it doesn't if it doesn't go into solution, or if it forms precipitate with HCl, you're going to get either a silver, lead, or mercury. And you can know this by simply just looking at a solubility chart. So let me Google that for you here, and you'll be given this on like a specific test or anything. And as you can see in Cl here, it's soluble except silver, mercury, and lead, and that's why they got here silver, mercury, and lead. And it forms a precipitate with chloride with all these three cations. Otherwise, it's soluble, right? So otherwise, it goes into solution here. If we're adding H2S, an acidic solution again, we're going to get these guys here are going to be insoluble here. These guys are going to create a precipitate because, as you can tell with sulfur here, it's insoluble except for group 1, 2, and NH4 here. So in this case here, these guys here are going to be like insoluble in water. Sorry, yes, insoluble in H2S here because it's a acidic solution. And then afterwards, we're going to add a basic condition here. Under a basic condition, a precipitate is going to be including these metals here. So aluminum, cobalt, iron, nickel, and manganese, and zinc would then precipitate and not be soluble in solution. And then finally, if we're adding sodium, I believe it says sodium carbonate here into our solution, we can see that in our solubility table, sodium carbonate would be insoluble except for group 1 and NH4. So group 1 would be barium. It would also be barium is group 2 here. So this is insoluble except group. This should be group 2 here. So maybe let's look at another solubility table to confirm the solution here. And I just want to see, nope. Let's look at these rules here. Let's look at carbonate. So this is CO3. Since their carbonates are frequently insoluble, group 2 carbonates are insoluble here. So this means that it precipitates out. So barium, calcium, magnesium, these are all group 2 metals. So as you can see in the periodic table, these are group 2 metals, right? Barium, calcium, magnesium, these are all group 2 metals, therefore they'll form a precipitate, and all the other metals are not the other metals will be in solution. So for example, sodium, potassium, and ammonium are going to be in solution. So the solution here is correct. I like how they broke down into specific steps here to kind of test your knowledge of solubility chart charts, but all you have to do is kind of go back to these rules and figure out which of these are soluble and insoluble in acidic or in basic conditions, and also with specific polyatomic anions such as carbonate, and also with such as carbonate. Yeah, that's about it. So this solution therefore is correct. So so the solution here is correct. Analysis. I really like how they broke this down as well. It's a very detailed and very clear way of doing this. Okay, let's look at number 2. So number 2 is, what is a neutral atom? And we can define basically a neutral atom as an atom that has the same amount of protons and electrons. So therefore the charges are balanced out, so therefore it's a neutral atom. So I can define this as, same amount of protons and electrons. So that would give me a neutral charge. So therefore it becomes a neutral atom. And that's kind of the definition of what a neutral atom is. So as you can see here, because we have protons here which are positively charged, so this guy here is positive charge, electrons are negatively charged. If we have the same amount of both protons and electrons, then therefore we have a neutral charge. So therefore it says here number of protons equals number of electrons, so the solution here is correct. So for example, in this atom here, which is it has 4 protons and 4 electrons, so therefore it's a neutral atom here. And if you have an imbalance of them, it could either be a positively charged ion or a negatively charged ion here. So the solution here is correct. Okay, let's look at number 3 here. It says define and provide an example for each of the following. So we have atomic element. We have molecular element. And then we have ionic compound. And then we have molecular compound. So what we have here is an atomic element, honestly, any element on the periodic table. So if you look at these elements in the periodic table, like an atomic element, for example, calcium would be an atomic element here because it exists only in 1 unit. So it'd be a calcium, it could be lithium, for example, it could be carbon. All these guys here are atomic elements because they exist as one. In a molecular element, however, for example, these guys exist in 2. So these are commonly known as diatomic molecules. So, diatomic. Let me read. So these are known as diatomic molecules. And we like to use a mnemonic for diatomic molecules, so it's Hofbrinkel. So Hofbrinkel. So hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. All of these guys here exist in 2. So for example, I would have H2 or O2 or Br2. And these guys are all diatomic molecules, which means these are molecular elements. Everything that's not a diatomic molecule would be classified as atomic element. And then ionic compounds are a mixture of non-metal and a metal, or a cation plus an anion here. So if I were to give you an example, NaCl is an ionic structure because I have Na plus and Cl minus. Let's do magnesium chloride, for example, has Mg2 plus and Cl minus. All of these guys here are ionic compounds. So that's a non-metal, metal, or cation and anion. And finally, in a molecular compound, these are typically a non-metal plus a non-metal. So for example, you have CO2, carbon dioxide. You would have something like, let me try to think of another one here. N2O5 would be another one here. This is dinitrogen pentaoxide. And these guys are reliant on covalent bonding. So they share electrons within within their the compound here, and typically it's a nonmetal plus a nonmetal. So in summary, we have atomic element is basically any element on the periodic table that exists as one individual element. Molecular elements are not commonly known as diatomic molecules, which means they can exist in two. So you have the mnemonic Hofbrinkel. So hydrogen, oxygen, fluorine, and other gases exist as two. So these are molecular elements. A compound is simply a nonmetal and a metal, and molecular compounds are a nonmetal and a nonmetal. So these are just examples of those guys here. So the solution here is, I believe, is correct. Let me just check. Atomic element has a single unit. That's good. Molecular unit has two or more elements, which is hydrogen gas. That's good. Ionic is metal bonded to nonmetal. Molecular metal is two or more nonmetals bonded together. So solution is correct. Good analysis. Let's do question 4. I want the systematic names of these compounds here. And as you can see, the solution is, I don't know what they're talking about here. I think it's a maybe transcription error or something like that, but I can't read that. So, yeah. So let's just, I guess let's just use problems together then. The solution is probably a different format. So I have here, I want the systematic names for compounds here. So A, I have CuIS. B is Fe2O3, solid. C is COF2. And D here is FeOS. So all these guys here are going to be, they're all multivalent metals. So this metal here, multivalent, 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 which means they can exist in one or two more charges. So we need to figure out, okay, how do we figure out these charges here? So what I would do here is I can kind of think of this as, I can dissociate or break down this compounds into its ion form. So I have Cu plus and I minus on this one. I have Fe something, I don't know this charge here, and O2 minus. Well, in this case for copper, for A here, let me go back to copper here. I know it's 1 plus here because I'm going to have to balance this 1 minus charge here, right? So this, I would have a charge of 1 plus here. If I have a 2 minus charge here, if I do the crisscross method, O3 would make a 3 plus on the iron, right? So I would have 3 plus here, and this would be 2 minus. CO, I have F minus here, and this F has a 2 coefficient of 2, so therefore cobalt should have a charge of 2 plus. And then FeO, O here has, I have a charge of 2 minus, which means iron has a charge of 2 plus. So if I know the charges of these guys, I can simply write down the name, right? So for example, this guy here is copper. Cu is copper, and the charge here is a 1. So I have to indicate the charge, copper 1 iodide. So very similar to how we label ionic compounds, because we have a metal and non-metal, but we, in this case here, we have to also label or denote the charge here. This one would be Fe, which is iron, and then I have a 3 charge, 3 oxide. This one would be Co, which is cobalt. This would be 2, and then fluoride, and then finally this one would be iron 2 oxide. So these guys here are the systematic compounds, or the systematic names for these compounds. So I'm going to say formatting issue with solution. I'll just type it out. A is copper 1 iodide. B is iron 3 oxide. C is cobalt 2 fluoride. And D is iron 2 oxide. And the solution in here is incorrect because I can't see the solution. This is number 4. Number 5 says complete and balance the equation for this reaction in an acidic condition. And it's asking us now which element was oxidized, which element was reduced, which species was the oxidation agent, which one was the reducing agent. this is number 5. So I have, let's write down this equation here. I have ZnS plus NO3, sorry. NO3 minus would yield Zn2 plus, or Zn2 plus, sorry, plus S plus NO. Okay, so in order for us to solve this problem, they didn't actually do a step-by-step solution here, which is unfortunate. We actually have to write down the half reactions to figure this out. And again, this is in acidic conditions here. So keep that in mind. So let me write down the half reactions first. So I have ZnS. There should be a charge on S here, but I don't. It doesn't say that they have a charge here. So I'm just going to write solid sulfur. ZnS is going to dissociate into Zn2 plus S here. And then I have NO3 minus is going to dissolve into NO here. And what we want to do first is we want to balance out anything that's not hydrogen or oxygen. In case here zinc is balanced, here sulfur is balanced, and nitrogen is also balanced. So now we have to move on to our oxygens. As you can see in the first half reaction, there's no oxygen, which is fine, but the second one does, right? I have 3 oxygens here and 1 here, which means I have to add water, right? So I'm going to have to add 2 waters to this guy here to make 3 oxygens balanced. But now, as you can see, we have a different problem here. We have 4 hydrogens on this side, and I'm going to have to add hydrogens on this side as well. So, which means I'm going to have to add 4H plus to the side as well. And now what we can do is, if I balance out the hydrogens and the oxygens, I have to balance out the charges as well, right? So let's balance out the charges. So I have ZnS plus yields Zn2 plus and S. So I have a 2 plus charge here and I have a neutral charge here, which means I'm going to have to add 2 electrons to the side. And then for this side here, this is a 0 charge here, and I have, this is -1 plus 4, which is -3. So therefore, I'm going to have to add, a plus 3 on 3 electrons on this side here, which in this, or actually, sorry, this would be a, yes, this would be a -3, I believe. Sorry, this is a +3, so I have to make this a -3, which means I have to add 3 electrons to the side as well. And then what I can do is I want to balance out the electrons. So I'm going to have to multiply both equations by, the first equation by 3 and this equation by 2 here. So this here becomes 3, 3, 3, and this would be 6. So let me erase this. And the reason why I do this is because I need to balance out the electrons here. And I'm going to multiply all of this guy by 2. So this here is 2, this here is 2. This here becomes 4. This here becomes 2. Or sorry, this here becomes 8. And this becomes 6 here. This is 6 here. Now what we can do is we can simply put both of the equations together, right? So I'm going to have 3ZnS plus 2NO3 minus plus H plus 6E minus is going to yield, I'll write it on a different line here, 3Zn2 plus 3S plus 6E minus plus 2NO plus 4H2O. And as you can see here, the electrons are going to cancel out, which is great. That's good. And we are left with the following equations. So we can say this is going to be equal to 3ZnS plus 2NO3 minus plus 8H pluses is going to yield 3Zn2 plus 3S plus 2NO plus 4H2O. And this here is going to be our equation. And as you can see, this equation is correct because we have 3ZnS, 2NO3 minus, 8H pluses, 3Zn2 pluses, 3 S's, 2 NO2s, and 4 H2Os. So this balancing is correct, which is great. Now we have to point out, okay, which element was oxidized, which element was reduced. So let's look at our rules here. And remember, our rule says Leo and Jer here for This is the mnemonic for our oxidation reaction. So we know that the loss of electrons is the process of oxidation, and the gain of electrons is going to be reduction. So what we can see is if we look at our half reactions here, our Z and S here is going to be losing electrons, right? And NO3 is going to be gaining electrons, so which means the sulfur is going to be oxidized here. I'm losing electrons on the sulfur, which is good. So this is oxidized, and N here is going to be reduced because I'm gaining electrons, right? 2 NO3 plus 6 electrons, which is good, which means my my oxidizing agent is going to be NO3, and my reducing agent is going to be ZN. S here, which is correct as what they did here. Remember, the reducing agent is the one that's being oxidized, and the oxidation reagent is the one that's being reduced. So this solution here is correct. It's a good analysis as well. Actually, I guess there's no analysis, so just say solution is correct because they didn't really give us the step-by-step format for this. So the solution here is correct. Okay, let's look at number 6. Just calculate the molar solubility of barium fluoride in each liquid or solution. So we have barium, BaF2, barium fluoride, and I want to calculate it in pure water. B is 0.10 molar of barium nitrate, and C is 0.15 NaF. Okay, so I'm looking at the solution here, and it's an incomplete solution because I don't really know, I don't really see any numbers here, so this is going to be an incomplete solution. Again, I don't know what the molar solubility here is as well, so that's no good. So let me just look at the question here, see if they give us any additional information. And they do not. So this one here, so this here is, again, an incomplete solution because I don't have anything here. So we're actually going to have to just solve this problem by ourselves here. So let's calculate the molar solubility of barium fluoride in each liquid or solution. So we're given pure water first, and then we're given these two guys here. So in order for me to calculate this, I'm not given any concentrations here, right? So for pure water here, so I'm not given anything for pure water, but I'm given some concentrations for these guys here. I have 0.10 molars of barium nitrate and 0.15 molar of sodium fluoride. So in pure water, for A here, I would actually just have to look up the molar solubility for barium fluoride in pure water, because I'm not given some specific concentration here. So let me look that up for you. Molar solubility of, this is barium fluoride. So let's see. In this case here, I would need to know the KSP of our solution here. So give me a second here. We need to know the KSP of barium fluoride for us to solve for this problem. That's going to be, let's look at barium fluoride is 1.0 times 10 to the negative 6 here. So that's going to be our molar solubility for that. Let's look at our solution then. So let's see here. 1.0 times 10 to the negative 6. And let's see here. Yeah, so what we have here is we need to know our KSP. Our KSP is equal to, according to this soluble, according to this KSP table here, barium fluoride has a KSP of 1.84 times 10 to the negative 7. But this one says 1.0 times 10 to the negative 6. So let me just find you a good number here. Yeah, it's one. So two of them have, say, 1.84 times 10 to the negative 7. So I will go with that. .84 times 10 to the negative 7. So if we know our KSP here and we know it's in pure water, what we can do is we can simply just create an ice table, right? So we have our chemical equation here. BAF2 is going to dissociate into BA2 plus 2F minus, right? And then what we can do is we can write our ice table for us to solve for that. So again, we're not given our initial concentration, so we don't know that, but we know we start with 0 and 0 for this. So we're making some type of concentration here. And what we can do is we can calculate the molar solubility because we're given our KSP value, right? So KSP, we can say, is equal to the concentration of our reactants, which is Ba2 plus, times F minus to the power of 2. And the reason why this is to the power of 2 because we have the coefficient of 2 here, right? So we're going to have, this is plus 2x for the coefficient of 2 here. That's my fault. This is 2x and this is 2x here. So this is going to be x times 2x squared, which will give us 4x cubed. And this will equal our KSP value of 1.84 times 10 to the negative 7, right? So we can say that 4x cubed equals 1.84 times 10 to the negative 7. And what we can do is divide both sides by 4, right? So we have 1.84 times 10 to the negative 7 divided by 4, which will give us x cubed is going to give us 4.6 times 10 to the negative 8. And therefore x would equal to 3.58 times 10 to the negative 3. And this will be our solution for the pure water solution for the molar solubility of barium fluoride. And it really depends on this KSP value. Because I don't know this KSP value, it's very, very hard for us to solve for this problem. So I don't know if this 1.84 times 10 to the negative 7 is good or not. So I'm not sure about that. But we can do the other problems as well. We can do 0.10 and 0.15 very, very easily because we can write them out as a chemical reaction and simply do an ice table again. So let me say that the solution is missing information. Part A, I would have if KSP of BAF2 is 1.84 times 10 to the negative 7, then molar solubility is, I solve this as 3.58 times 10 to the negative 3 molars. And then for B, I would have to solve for B here. So let me just clear this up. Let's solve this for B. And B here says, so this is still question 6B, 0.10 molar of BaNO3, 2 here. So what we can do here is we can, let's see, we can do we can basically relate barium nitrate and the moles of barium nitrate with the moles of barium fluoride, right? So if we have BaNO3 2 and this dissociates into, again, Ba2 plus this would be NO3 minus, I'm going to have 0.10 molar of this guy here, but I'm going to have Ba2 plus, which is also 0.10 molar. And then I have this nitrate group, which is going to be 0.20 molar actually because of that coefficient of 2, right? But I really care about Ba2 plus because this is going to be related to my barium fluoride, right? Because I wrote this as Ba2 plus F minus 2F minus here. And again, because I have 0.10 here, I can actually solve, I can use my ice table now, right? So if I have a concentration here, I don't know these guys here, but I know now Ba2 plus is 0.10, right? And this one here is, I know as 0. I'm going to get minus x, or plus x, sorry. This is still 2x here. So I have 0.10 plus x and 2x here. And now if I'm given my KSP value of barium fluoride, which I assumed was 1.84 times 10 to the negative 7, I can solve for this problem again, right? So KSP is going to equal Ba2 plus F minus to the power of 2, right? And this here, now I have 0.10 plus x. And this one would be 2x squared. Which means that this here is going to be, I have 4x squared multiplied by 0.10 plus x. And this here would be 0.40 x squared plus 4x cubed would equal my KSP value of 1.84 times 10 to the 7. And all I'm going to do is simply isolate for my x value here to solve for this problem. And what we can do here is we can actually just factor it. We can factor out this, we can factor in x squared here. So 0.40 plus 4x. Or actually, I would actually have to move this to the other side and do a kind of a cubic kind of relationship. If I want to avoid this kind of problem here, I can actually use the assumption method and say that this here is very, very small. So I can just simply cancel that out. So that might be a bit easier for us to solve for this problem. So I'm going to have simply just 4x squared times 0.10, which is 0.40 x squared. I can divide both sides by 0.40 to get that alone here. So I have 1.84 times 10 to the negative 7 divided by 0.40. So it gave me 4.6 times 10 to the negative 7. And I can simply square root that number to give us our molar solubility, which is going to be 6.78 times 10 to the 4 molars here. And this is going to be our solution for B. So I'm going to say, I'm assuming that this KSP value is correct here. It's all based off this assumption. Molar solubility is 6.78 times 10 to the negative 4. And then let me do 6C here and I'll clear this. And it's very, very similar to B and what we've been doing before. So I have 0.15 molars of NaF. So if I look at NaF here, I can write a chemical equation and say that I have Na plus F minus here. And we have 0.15 molarity of our sodium fluoride, right? So I have 0.15, which means these guys are also 0.15 here. So what I can do now is I'm focused on this guy here, right? Because I need to relate it to my barium fluoride. So again, this is BF2, Ba2 plus 2F minus. And if one F minus is 0.15 here, what I can say here is I can say that 0.15 also exists in this solution as well. So this here is 0.15, right? And this here would be 0, and I don't know these guys here. And again, I'm doing my ice table. So I can draw my ice table. I'm starting with 0 barium, but I'm starting with 0.15 fluorine from the sodium fluoride here, right? So again, I'm adding x here. This would be 0.5 plus 2x. So that leaves me with x and 0.15 and 2x here. Again, I can write my KSP values. So I have 1.84 times 10 to the negative 7 is going to equal the concentration of barium 2 plus plus the concentration of fluorine minus to the power of 2. It's going to equal x times 0.15 plus 2x. And this would be squared. And then what I can do here now is I can, if I wanted to, I can factor this out, and well, I can FOIL to get an algebraic solution here. But what I'm probably going to do is I'm probably going to assume, again, the small x approximation. So this 2x is going to be, I'm going to assume that this is going to be very, very small. So x here is going to be simply just 0.51 squared, and I'll be able to solve for this value here. So I can divide both sides by 0.15 squared to get my x value. So I have 1.84 times 10 to the negative 7 divided by 0.15 squared here. And this would give me a value of 8.17 times 10 to the negative 6. And this is our molar solubility for part C. So it all depends on our molar solubility, on our KSP. I'm hoping that this KSP is our correct, the correct one, because we're not given our molar our KSP value for this problem here. So I'm basing my information off this KSP value here. So the solution here is incorrect because it's an incomplete solution. All right, let's look at number 7. So 7 is asking us, will NH4F be acidic, basic, or neutral in water given pKb of NH3 and Ka of HF here? So it's asking us acidic, neutral, basic, or neutral, and asking us what is the final pH of a solution that has 0.123 molars of ammonium fluoride. So let's look at the solution here. And what they wrote down first is they wrote down the dissociation, which is great because that's kind of the first step into every equilibrium problem. So if NH4F is going to dissociate into NH4 plus F minus here. And then what's also in equilibrium is this NH4, right? Because this NH4 is also, if I add H2O, because it's in water, it's going to dissociate into, it's going to be in equilibrium with NH3 plus H3O plus. And that's very important as well. And that's what they're doing here as well. And they also wrote an equilibrium reaction for the F minus here. So F minus plus H2O also get me HF plus OH minus. So F minus is simply the conjugate base of our hydrofluoric acid. So therefore you have, again, NHF is NH3 plus HF here, which is good. They simply just combine both of these reactions together. So what they're doing here is they're using the Henderson-Hasselbalch equation. So pH equals half. Is this the Henderson-Hasselbalch? Let's see. Oh, this is not the Henderson-Hasselbalch. I don't know which reaction which formula they're using here. It's half times pKa of NH3 plus pKa of HF. And I don't know if we're given the Ka here, so we can actually solve for the pKa here. I don't know what this formula comes from. This is half of pKa here. So let me just Google this. Half of pKa. Because this one is Henderson-Hasselbalch, so I don't know what this formula here is. Yeah, I don't think I've ever seen this formula before. pH equals half of pKa plus pKa. So I'm not sure about this formula here. Because I'm solving for the pH here, but it's not determinant of, it doesn't rely on my pH here, it just relies on my pKa. So this solution here is incorrect here. We can actually use so what I was talking before, we can actually use the Henderson-Hasselbalch equation. So we have pH equals pKa plus log of base over acid. So our base HA over our acid A minus here. And this is the correct formula for Henderson-Hasselbalch. I don't know what kind of this formula here is, but it could be valid, I'm not sure. But again, my answer doesn't rely on the concentration here, which worries me a little bit. Our pKa here is 4.75, or sorry, this is a pKb value, so I have to find a pKa value, which is 14 minus 4.75. So pKa is 14 minus pKb. It's 14 minus 4.75, which is 14 minus 4.75, which is 9.25. And then we can figure out our pH using the log of base over the concentration of base over acid here. And I don't think we're given a concentration of our base here. But I think what we can do is, instead of using this, we can actually use an ice table. Because I'm not giving my concentration of acid and base, I think I'm going to just simply use an ice table instead. So let me just erase this. Because I'm just going to use an ice table and then solve for the concentration of our hydronium ion instead. So let's see. So I'm going to use this first formula here. Let me just erase this as well. And then I'm simply just going to do an ice table instead. Again, I was going to do a Henderson-Hasselbalch because I saw the solution, but I think an ice table is a little bit more appropriate here. So I'm starting with, again, if I start with a 0.123 of ammonium fluoride, I'm going to start with 0.123 molarity of our ammonium here as well. Water does not, I don't care about my water in my equilibrium reaction. I start with 0 and 0 here. So I have minus x, so I have 0.23 minus x. I gain some type of concentration here, which is great. And then what we know is our pKb of our ammonia is 4.75. So we can actually write down our Ka value here, because I have ammonium. So I'm going to have to actually translate this. So what I can do is I can do the same thing. So I can say pKa here is going to equal 14 minus pKb. So pKa is going to, I think I solved for this as 9.25, which is good. And I'm going to translate this back into Ka. So Ka is simply just, Ka is going to be the 10 to the negative 9.5 here. It's simply just negative log of Ka. pKa is negative log of Ka, so Ka has to be 10 to the negative pKa. So negative 10 to the power of negative 9.25 here, which is going to be 5.62 times 10 to the 10. And given our Ka value here, we can actually solve for x value, which we can solve for our hydronium ion, which will give us our pH. Sorry. This is 10. So this is going to be the concentration of ammonia, NH3, and water divided by our concentration of ammonium. We know that this is x squared divided by 0.123 minus x. I'm going to use a small x approximation again. So this is going to go away. I'm going to simply just multiply both sides by 0.123. So I'm going to get 6.92 times 10 to the negative 11 on this side. And then we square root both sides to get our concentration of hydronium, which is 8.32 times 10 to the negative 6. And this will equal our concentration of our hydronium, right? This is the molar solubility for this compound. So we can do simply pH equals negative log of our hydronium here. This is going to equal 8.32 times 10 to this negative 6. This is going to equal, should equal our answer, which is 5.08 here, which is not what they got here. 5.08. And this here is our pH for this solution. So this is 5.08, assuming that this was only for the ammonia, but I believe that we need to assume we also have to talk about our conjugate base, which is our F minus here. So I think I have to basically repeat this step for F minus, and then we can solve for what the POH for that one is, and then look at our two values for that compound. So I think that's why they wrote half, because it's halfway of both sides, but I think that might work as well. So let me have to look at the solution. I think that this equation actually holds because it's an amphoteric substance. So that's why I don't actually care about the concentration here. So I believe that equation actually will hold for amphoteric substance. So let me just write down what I would do, because I have, again, 0.123, and then I'm basically creating another ice table here. So this is 0.123, or sorry, minus x. 123 minus x. This would be plus x and plus x here. And then I would basically do my, I have a Ka of HF here, but I need my Kb value because I'm working in in OH minus. So what I would do is I would actually find the Kb value by simply doing Kb equals Ka times Kb here. And this is Kw. Kw is 10 to the negative 14 times 6.6 times 10 to the negative 4 times Kb. Therefore, Kb is going to equal 1.0 times 10 to the negative 14 divided by 6.6 times 10 to the negative 4. This is kind of two questions. One, it's a very long question here. So I'm going to 1.52 times 10 to the negative 11. And now we can write out our concentration, right? Because I can set this to my Kb. So 1.52 times 10 to the negative 11 is going to equal the concentration of OH minus and HF divided by F minus here. This is x squared divided by 0.123 minus x. We can use a small x approximation again, so I'm just going to simply multiply both sides by 0.123. So I'm going to get 1.86 times 10 to the negative 12 equals x squared. Square root both sides. I'll get my molar solubility, which is going to be 1.36 times 10, or 1.37, sorry, times 10 to the negative 6 molarity, which will equal my concentration of my hydroxide ion. And then what I can do is I can solve for my POH here. So POH is negative log of my hydroxide ion. So it's negative log of 1.37 times 10 to the negative 6, which is going to equal 5.86. So let's see, I have 5.86 for this guy here. So pH would be 14 minus POH, which is simply 14 minus that number, which is 8.13. So I have here 8.13 and 5.08. So it should be halfway between these two values here. So I have 5.008 plus 8.13 divided by 2. And this would give me my my solution here. And this would be 6.605. And I believe this one would be our correct answer based on those concentrations there. So very, very close to what they got here. But again, I'm not sure if this equation holds for this this formula. Let me just do a quick Google search. Amphoteric substances half pKa plus pKa. pKa formula. Yeah. So I'm actually quite unsure about this formula here. So I'm going to say solution is incorrect, and I'm gonna base it based off of my two ice tables here. Doing two ice tables with both NH4 plus and F minus gives me pH values of, this is 5.08 and 8.13 respectively. The average pH value would be 6.61, which is close to 6.215, but not quite. I am unsure about the formula you used for amphoteric substances. Substances where pH equals half times the sum of pKa values. So I'm just saying the solution here is incorrect. Okay, I think that's enough chemistry for today. Again, I only got through 7 questions today just because, again, this question was very, very long and they didn't really provide a great solution for us, but I'll pick off where we left off probably next week as well. Again, thank you so much for watching. Again, my name is Joey. If you like these YouTube channels, YouTube videos and live streams, definitely check us out at youtube.com/OneClass, and you'll be able to access those videos as well. Again, thank you so much for watching. Stay safe, stay healthy, and have a good day. Take care.